Welcome back, everyone. All right, let's jump right into Chapter 7 of our source material for today's explainer. We're looking at the transformation journey, forms of energy, and their uses. Energy is quite literally what makes the world go round. It's the hidden driver behind every single movement, every spark of light, every sound we hear. In this explainer, we're going to break down exactly how energy moves, how it's stored, and most importantly, how it completely transforms from one state to another to power our entire world. Let's get into it.
So, what do running a vehicle, lifting a heavy weight, and rotating a fan actually have in common? Think about it for a second. While they might seem like completely unrelated things, the common thread tying the whole shebang together is the fundamental scientific concept of work. In our day-to-day lives, humans, animals, and machines are constantly engaging in different types of work. But to actually pull off any of this work, whether it's an engine burning fuel to push a car down the highway, or just your own muscles contracting to lift a box, you absolutely need energy. You literally cannot have work without energy. It's a package deal.
Okay, here's our quick roadmap for today. We'll be breaking energy down into 4 main categories. First up, work and mechanical energy. Second, electrical, sound, and light. Third, heat and power generation. And finally, number 4, the power of chemicals.
All right, starting with number 1, work and mechanical energy, the basics of motion.
Let's look at the contrast between 2 fundamental states of energy, kinetic and potential. Our source material uses a really great, relatable image here, water. Think of a fast-flowing water stream. That movement, that is kinetic energy. It's literally the energy of motion. Because the water is actively moving, it's got the kinetic energy required to actually do work, like, say, turning a water wheel. But where does water get that energy to begin with? Well, that brings us to potential energy, which is just stored energy. Imagine water resting quietly at a higher elevation, like right at the top of a waterfall. Just by being up high, it has the potential to flow downward, right? The split second it drops, boom, that stored potential energy is instantly transformed into kinetic energy.
Now, the crucial point here is how these 2 concepts, kinetic and potential, tie together. Together, they fall under one big overarching term, mechanical energy. To really picture this, imagine the textbook's example of a simple toy cart resting on a table. While it's just sitting there minding its own business, it possesses potential energy relative to the floor. But if it rolls off the edge, that potential energy converts straight to kinetic energy as it falls. So both that resting state and that moving state fall under the grand umbrella of mechanical energy. Moving on to part 2, electrical, sound, and light, the energy we experience.
Energy rarely stays in just one form. It absolutely loves to transform. Think about a standard radio. When you turn it on, it takes electrical energy, whether that's from a wall outlet or a battery, and transforms it directly into sound energy. And yes, our source material makes a point of noting that sound itself actually contains energy, which we can scientifically observe. For instance, if you place a piece of paper near a loudspeaker, you can actually see the paper vibrating. That vibration, that's the sound energy doing actual physical work. And just like that radio, everyday sources of light rely on specific materials to fuel these transformations. We've pulled this table directly from Chapter 7 of the text. An electric torch or a flashlight requires dry cells, batteries, to produce light. A candle relies entirely on the wax it's made of, and a traditional kerosene lamp needs, well, kerosene. In every single one of these instances, a specific material is being consumed to kick off an energy transformation that ultimately gives us light energy. Now, light is obviously crucial for vision, but as we're about to see, the core principles used to generate it can be scaled way, way up to power entire cities.
That brings us to part 3, heat and power generation, scaling up. To really grasp how heat turns into power, our source textbook lays out this brilliantly simple classroom activity. Picture taking a small tin can with a tiny hole bored into the lid and putting a little bit of water inside it. Now, place this can over a burner. Step 1, the water heats up. Step 2, as that water boils, high-pressure steam escapes right through that tiny hole. And step 3, if you suspend a small homemade turbine, like aluminum blades stuck into a cork stopper, right above that hole, the escaping steam is going to aggressively rotate those blades. It's awesome. You have just used heat energy to create steam, which then provided the kinetic energy to do the mechanical work of spinning a turbine.
Now, what's truly fascinating is how we scale that exact same tin can experiment up to the real world. This diagram straight from the source shows the inner workings of a thermal power station.
Instead of a tiny tin can, you have a massive industrial boiler. Instead of a little lab burner, you've got tons of fuel like coal generating immense heat. That heat boils water into high-pressure steam. Then that steam is piped directly into a giant turbine, causing it to spin at just incredible speeds. This spinning turbine is hooked up to a dynamo or generator, which then churns out the electrical energy that gets sent through power lines right to your house. It is literally the exact same principle as the tin can, just on a magnificent, massive scale. To really appreciate the magnitude of this stuff, just take a look at this incredible photograph from our text. We're looking at a worker inspecting the blades of a real-world turbine inside a power station. I mean, look at the sheer size of that machinery. This single image perfectly captures how human engineering harnesses mechanical and heat energy. The steam rushes past those countless metal blades, forcing that entire massive cylinder to rotate. It's honestly a beautiful, awe-inspiring reminder of the heavy physical machinery required to generate the invisible electricity that we use every single day without even a second thought.
And finally, Section 4, the power of chemicals, stored potential. Now, it might surprise you to see some of these everyday items grouped together. What exactly do a plate of food, a simple dry cell battery, a matchstick, and a bomb all have in common? Well, they're all densely packed vessels of stored chemical energy. The textbook highlights that chemical energy is just sitting there, waiting to be released to do work. The food you eat, it contains chemical energy that your body breaks down to give you the kinetic energy to walk around and move. Firewood stores energy that when you light it, releases heat and light. Firecrackers and bombs store highly volatile chemical energy that releases massive amounts of sound, heat, and kinetic energy in an absolute instant. It's all just stored potential, waiting for the right catalyst to transform. Which brings us to our final provocative thought for this explainer. Look around your immediate environment right now. From the food currently digesting in your stomach to give you heat and movement, to the chemical battery draining inside the very device you are using to watch this explainer right now, what other energy transformations are happening around you in this exact moment? Seriously, think about it. Once you really understand the journey of energy, you start to see the entire world not just as static objects, but as this endless, fascinating web of kinetic, potential, electrical, and chemical transformations. Keep observing, keep learning, and I'll catch you on the next explainer.